In this video, we'd like to introduce our paper Social NCE, Contrastive Learning of Socially Aware Motion Representations. Anticipating the motion behaviors of others is an essential ability in the social context, like the dense traffic shown in this video. However, building machines capable of doing so is not easy, due to spatial-temporal interactions among multiple agents. Oftentimes, these interactions are too complex to describe by handcrafted mathematical models. In the past few years, researchers have proposed a variety of neural network models to learn motion representations from data. The learned models usually work pretty well in single-step predictions on the holdout test set, but struggle to generalize to the long-range closed-loop operation. Even state-of-the-art models still output unacceptable solutions, like collisions. Why is it difficult to learn a robust motion representation? The key challenge stems from two sources. Number 1, sequential prediction is not an IID problem. As illustrated in this figure, while the training trajectory in blue and the test trajectory in red start from the same state, these two trajectories may gradually diverge due to the prediction errors accumulated over time. As such, the state distribution at test time is not identical to that during training, but rather dependent on the learned model. Number 2, training data is often severely imbalanced. Existing real-world datasets usually come from natural observations, where humans rarely enter dangerous regions. The combination of these two sources poses a significant challenge. The sequential model is trained in safe scenarios but tested in more dangerous ones. It's known that conventional machine learning models are not good at out-of-distribution generalization. Given such an ill-distributed training data, how can we learn a robust model for closed-loop sequential prediction? In this work, we aim to address this challenge by promoting robust motion representations through self-supervision. Our key idea is to explicitly model negative examples based on our prior knowledge. Intuitively, one effective way to explain the social norms behind positive examples is to portray the opposite negative examples like collisions. We formulate this intuition into a new learning framework that consists of two components, a social contrastive loss and a negative sampling strategy. Let's first have a close look at the social contrastive loss. Most recent forecasting models are built with encoder-decoder-based neural networks, where the encoder extracts a representation of the past observations, and the decoder rolls out the future trajectory recursively. The model is typically trained with a task loss, such as mean-squared error. In order to promote robust representation, we introduce an auxiliary loss, which regularizes the feature vector such that it contains sufficient information for distinguishing a positive event from a set of negative ones. The event is defined as the state of the agent at a specific time step in the future. We formulate this objective as learning an embedding space, where the projected feature vector of the history is pulled closer to the embedding of the positive future events while pushing apart from the negative ones. One crucial component of our method is the design of positive and negative samples. Recent contrastive methods in vision and language problems often rely on carefully designed data augmentation for positive pairs while using random samples to form negative pairs. However, this design choice is not suitable for motion problems, since it does not bring more information than the main task about social norms. To more explicitly fill up the shortage of dangerous scenarios in the training data, we propose to draw negative samples from the neighborhoods of the other agents in the future, given that one location is rarely occupied by multiple agents at the same time. Our method can be viewed as a form of negative data augmentation through self-supervision, as opposed to laboriously collecting additional state action pairs from dangerous scenarios. We validate this method on a variety of tasks in the multi-agent context. On the forecasting task, our method significantly reduces the collision rate by a clear margin, without degrading the prediction accuracy and diversity. Qualitatively, our method tends to jointly adjust the trajectories of multiple agents and outputs more plausible solutions. We further validate our method in imitation learning for crowd navigation. Compared with conventional behavioral cloning, our method achieves better results, particularly in the low data regime, thanks to the additional information absorbed from the auxiliary contrastive task. We finally validate our method on Rainbow DQN, a state-of-the-art reinforcement learning algorithm. The agent trained with our method is more sample efficient. After 2K episodes, our agent is already able to accomplish the navigation task safely and efficiently, whereas the baseline agents crash with collisions. To conclude, we propose a learning method to promote robust representations for motion problems. The empirical results show that our method can consistently improve state-of-the-art methods in various settings. This suggests that learning from negative data through self-supervision can be a promising alternative to the classical approach for building robust sequential prediction. For more details, please refer to our paper and code in the following links. Thanks for your attention.